We're delighted to have Jacob Barandes from Harvard University, who's going to give this week's colloquium. Jacob was an undergraduate at Columbia University, where he was a double major in physics and math, and graduated top of his class, was valedictorian that year. He then went on to earn a PhD in theoretical physics at Harvard, working in high energy theory and quantum gravity. And his PhD thesis was on low energy landscapes arising in quasi-bound systems of multi-center black holes with exotic charges in 4-dimensional n equals 2 supergravity. So from the beginning of his PhD, Jacob has been interested in foundational and philosophical questions in physics. And after finishing his PhD, motivated partly by black holes and quantum information, his research shifted from high energy theory into philosophy of physics and quantum foundations. So in addition to his joint appointments in the physics and philosophy departments at Harvard, Jacob is a faculty affiliate with Harvard's Black Hole Initiative. And he also organizes Harvard's Foundations of Physics seminar series, as well as the annual New England workshop on the history and philosophy of physics. So in addition, Jacob is an excellent teacher and has won many awards for his teaching and advising. These include the Phi Beta Kappa Award for Excellence in Teaching, the Anya Bernstein Bassett Award for Excellence in Teaching, and the Everett Mendelsohn Excellence in Mentoring Award. He was also voted one of Harvard's favorite faculty members in 2003 and again in 2005. So today, Jacob's going to be telling us about what he sees as deep problems with quantum theory and how he thinks we should fix them. And so please join me in welcoming him.
Monica, thanks for the invitation. It's lovely to be here. We have a lot to talk about, so I'm going to get started. So my name is Jacob Barandes. Monica gave me a lovely introduction. Title of my talk is What's Wrong with Quantum Theory, How to Fix It. I'll explain the image a little bit later. This talk is based on a couple of papers. My papers show up on the archive and also on the Philosophy of Science version of the archive, the PhilSci archive. So you can find them in various places. They're currently under review. So it's not working all of a sudden. Okay. Yeah, okay. All right, so outline of the talk. Do some introduction. I'll talk about some problems for quantum theory. And I'll talk about a recently characterized class of physical processes called indivisible stochastic processes. And I'll talk about the detailed correspondence between these kinds of systems and quantum systems in the Hilbert-space representation. I'll have some things to say about causal locality. So if you're worried about Bell's theorem, we'll have lots to say about that. And then I'll conclude. In short, the first few sections are why you should care, what's going on. And then the last is detailing this new framework. All right, so that's some introduction. Here's some things people read or hear about quantum theory. And here I'm talking to faculty. I'm also talking to old friends, and I'm talking to students. We hear things like an atom doesn't have a position until you measure it. This is explicitly said at the beginning of David Griffiths' textbook, Introduction to Quantum Mechanics in section 1.2. An atom can be in 2 places at once. Particle takes every possible path from point A to point B. A single electron is also a Schrodinger wave. The whole universe is just a gigantic wave function. Every time you make a measurement, the universe splits. All you need to solve the measurement problem is decoherence. And there are more. Schrodinger's cat can be dead and alive. There's all kinds of things you hear. Are these statements objective facts, even though they're nowhere to be found in the textbook Axioms of Quantum Theory, as I will review shortly? And aren't directly seen, not directly seen in experiments, they're inferred from experiments. Are they interpretation dependent? One of the things people do in philosophy of physics is subject claims like these to rigorous scrutiny. And I know people think about philosophy, sometimes I think that philosophers like to engage in a lot of wild speculation. It's true, sometimes they do, and it's a lot of fun. But a lot of what philosophers of science and philosophers of physics do is actually the opposite, is subject claims to rigorous scrutiny. And that's what I'm most interested in. So just to give a brief introduction to myself, yes.
Yeah, how should I interpret colors? Like you've got purple and red, they seem to mean different things and I can't figure out what.
The colors are just so it's not just a wall of black text.
Okay.
Very roughly speaking, I do have in my mind like a color coding scheme, very rough. Red is like interesting action alert words sometimes, and purple is like concepts or terminology, and green is very important concepts and terminology or equations. There are only so many colors. Like people have their own color and dates have their own color. It's just how I keep track of what's going on. Yeah, but thank you. I thought your question about how you interpret color was like a philosophical question. We're going to get into a discussion about Frank Jackson's Mary's Room argument. What is a color? What is red? We can talk about those too, maybe the Q&A. Great question. We're off to a fantastic start. So, little introduction to me. What do I do? I have two sides in philosophy of physics. Roughly speaking, there is my philosophical physics side. You should read that as like mathematical physics or theoretical physics. It's a way of doing physics, but using the methods of analytic philosophy to apply rigorous scrutiny to our physical theories. Here are some examples. I like looking for cracks in our theories that may contain discoveries or surprises, pushing our theories to their logical limits. You know, a lot of people in this room push our theories to their mathematical limits or physical limits. I like to push our theories to their logical limits, and occasionally putting the brakes on wildly speculative claims. And there's a distinguished history of this. The people who gave us quantum mechanics and general relativity were steeped in and trained in philosophy. They spent a lot of their time talking about philosophy and writing about philosophy and arguing about philosophy, sometimes devolving into arguments about who was the correct vicar of Immanuel Kant and who was not. You know, Heisenberg wrote a book called Physics and Philosophy, and he's got whole chapters that are on analytic philosophy. Einstein was thoroughly trained in philosophy, Schrödinger. Yeah, one view is just if we want to recreate the incredibly fertile period in development of physics from that era, might not be a bad time to think a little bit about how to incorporate philosophy into what we do. The other side of what I do is physical philosophy. This is investigating what our physical theories bring to bear on traditional questions in metaphysics, like what do our physical theories tell us about time and locality and probability and causality. And both sides find many applications in quantum foundations, and I'll be talking about both of them here. So what is quantum foundations? It's the study of the fundamental physical, philosophical, mathematical, interpretational, and axiomatic structure of quantum theory itself. This area of basic research has had a controversial and sociologically complicated history. After a flurry of development in the 20s and 30s, the basic questions in the subject in quantum theory, the measurement problem, the interpretation of quantum theory, causation, locality, were sometimes cast as trivial or already solved or a waste of time or a matter of merely failing to understand it theory correctly. Or a system of lacking intellectual maturity or a mistake of taking things too literally. I'll say, though, that I've observed a positive generational shift in these attitudes that mirrored my own shift, having also come from having had these beliefs about quantum foundations. So I'm, for at least the next few months, the co-director of graduate studies for the physics department at Harvard, and I abused my power to require as a mandatory question in our intake survey for incoming physics PhD students some questions about foundations of quantum mechanics. The first is, what is your take on the measurement problem? Do you think it's a major ongoing problem or a minor ongoing problem? And you'll see from this list that almost half think it's either a major or a minor ongoing problem. The yellow slice there, the student who said it was a solved problem, I talked to the student afterward and asked what he meant, and he explained actually he thinks it's a major problem. So it's actually closer to half. Okay. What's your preferred interpretation of quantum theory? Let's play the interpretation game. And here you see a kaleidoscope of possibilities. Roughly half the students choose the orthodox or textbook or shut up and calculate interpretation, however you mean that. And a big next chunk take the Copenhagen interpretation, although because I think most students don't really know the difference between the two, those are almost synonymous. The next biggest chunk is the many worlds or Everett interpretation, and the rest occupy very small slivers of this pie chart. If you want to probe that further, we can do the Q&A. All right, well, so quantum foundations has had very few people work on it seriously over the past century. And there have been negative career effects on a lot of those people, David Bohm and Zay and Bell. Bell famously used to tell students not to work on it, or if they worked on it, to do it in secret. And there was no money for it. Nonetheless, it's had an enviable track record of important spin-offs that I would stack up against many other research areas. So obviously, famously EPR states, and I'll have something to say about those later, entanglement, quantum steering, and Schrödinger's cat. Decoherence. So this is a thing that a lot of people, I think, don't know. Decoherence was not invented by a practical-minded physicist or trying to get better like numerics. Bohm introduced decoherence in 1951 and then developed it further in his pilot wave interpretation in 52, explicitly because he was interested in the measurement problem. If you look in his 1951 textbook, there's a Dover edition, it's delightful. In chapter 22, Quantum Theory of the Measurement Process, he goes through a detailed analysis of the measurement process. And in section 22.8, which he calls destruction of interference, the process of measurement. He lays out basically the modern theory of decoherence as we recognize it today. Curiously, despite the fact that he really understood how decoherence worked, he invented it, he was not satisfied with decoherence. He recognized almost immediately that decoherence alone was not enough to solve the measurement problem. That's why he developed his pilot wave interpretation the next year, rediscovering work that had been done several decades earlier by de Broglie. All right, there's page 2 of spin-offs too. Wigner's friend, which we'll talk about, the Bell and CHSH inequalities, which went from metaphysics to actually being practical tools for certifying the randomness of quantum random generators, and are also used in like quantum cryptography. And, you know, rather, I think, relevant to recent history, won a Nobel Prize for Ospe, Clauser, and Zeilinger in 2022. The no cloning theorem, which was independently discovered by several people, including Dennis Geeks, who was absolutely a philosopher. Quantum contextuality, both from Bell's work and the Cauchy-Spector theorem from 1967. Quantum advantage and the Deutsch algorithm, which eventually became the Deutsch-Josha algorithm. So Deutsch introduced this in 1985, and his motivation for looking for quantum advantage was explicitly motivated by quantum foundations. In fact, this is the paper where he introduced it in 1985. Interestingly communicated by Roger Penrose. That's a nice little fact. And in this paper, he writes about a class of model computing machines. That is the quantum generalization of the class of Turing machines. It showed that quantum theory, the universal quantum computer, are compatible with the principle quantum computing, resemble the universal quantum computer could, and so forth. But the salient point is, and he says this several times in the paper, the intuitive explanation of these properties, the quantum advantages you get from quantum computers, places an intolerable strain on all interpretations of quantum theory other than Everett's. The story is that John Wheeler apparently had David Deutsch sit down with Hugh Everett, who had just come out of retirement briefly before dropping dead of a heart attack. They sat down together and had a long talk. And at first, Deutsch was very skeptical of Everett's theory. But by the end of dinner, his head was filled with ideas. And he's very clear that these ideas are what motivated him to look for quantum advantage. Sorry, page 3 of spin-offs. I'm sorry, there's just so many. There's so many spin-offs. I'm sorry. There's the no communication, no signaling theorem, weak measurements, quantum circuit diagrams, GHZ states, or GHZ states, depending on your background, the Elitzur-Weidmann-Baum tester, quantum causal models. So I just say, considering its input-output ratio, I mean, think about how often decoherence is used, or all the work going on in quantum cryptography and quantum teleportation and all that stuff. The input-output ratio of people and money, on the one hand, to spin-offs is actually pretty good. It's pretty good. I think it's worth people's time, at least some people, to think about this. All right, let's talk about problems with quantum theory. What are the things that people in quantum foundations are sometimes worried about? Well, just as an introduction, and this will be familiar to anyone who has recently read David Griffiths' textbook on quantum mechanics, in most textbook treatments of quantum theory, one takes the basic object to be a wave function or state vector in a Hilbert space over the complex numbers. And by axiom, this evolves according to the Schrodinger equation for some self-adjoint operator called the Hamiltonian. This is the Schrodinger equation in its general abstract form. I have another color. Brown is things that are law-like, related to laws. Nomological is the fancy word we use in philosophy for this. These are law-like things. The Hamiltonian is a law-like thing. You specify the Hamiltonian, you specify the laws of your system. And I should say that sometimes one instead takes the basic object to be a density matrix or a linear map on a C-star algebra, depending on your point of view. And then there's a host of other axioms, which we'll review, that provide an instrumentalist, meaning just a mechanical algorithm that you use to just generate predictions for using the state vector to calculate probabilities of measurement outcomes. And much of the interpretive debate lies within this wave function paradigm. It asks about the nature of the wave function. Is it epistemic, meaning knowledge about what we know? Is it ontological, which is a fancy way of saying, does it physically exist? Does it refer to something physical out in the world? Is it nomological? Is it an expression of laws or something else? And whether it should be supplemented with additional or replaced with hidden variables. All right, these are the Dirac-Feynman axioms. I want to put them on the screen here. Some of you know them. Some of you are just maybe starting off in quantum theory and either just learned them or haven't seen them before. But I think it's important to keep us all honest so that no one is playing around and moving goalposts as we go. So here are the axioms as you'll find them. And I'd like to break them into 5, but you can break them in other ways. So you have the axiom of quantum states. A quantum state is represented by a state vector or a wave function or a density matrix in the Hilbert space. If the system is closed, by which I just mean it is not interacting mutually with any other systems or exchanging information with any other systems, then by axiom, it evolves according to a time index family of unitary operators that make up what's called a time evolution operator. And if this time index family is strongly continuous in the operator topology, then there exists a well-defined self-adjoint operator called the Hamiltonian that generates that, and you get the Schrodinger equation from that. Those are the Hilbert space axiom, and then we have the measurement axioms. So each observable, according to the measurement axioms, is represented by a self-adjoint operator whose eigenvalues are the possible numerical measurement outcomes. You can generalize this to positive operator valued measures if you like. The Born rule provides a prescription, a formula for giving you the statistical average of measurement outcomes weighted by their measurement outcome probabilities. And if you stick in not a generic observable, but like a projector onto a particular eigenspace for an observable, then what the Born rule yields is the probability that you'll get that result if you measure the system. And then after a measurement, the quantum state collapses to the relevant eigenspace. It's projected down to the relative eigenspace, and this is intended to single out a unique measurement outcome. So again, the third axioms 3 through 5, the last 3 axioms, those are the famous measurement axioms. And I'll just say it here, but we're going to say it many times, and I'm sure people have questions in the Q&A about this. Decoherence does not eliminate axiom 5, because decoherence, as Bohm noted, doesn't single out a unique measurement outcome. It also doesn't create what's called a proper mixture. And if you want to know the distinction between proper and improper mixtures, that's a thing we can talk about in the Q&A as well. All right, so the derived Feynman axioms, they're instrumentalist. They give you a tool set for making predictions. And you could take a philosophical point of view that we don't like theories that are just instrumentalist. That's not what I'm going to be arguing here. I'm not going to be making a philosophical point here. I'm making a very practical point, a physical practical point. There are ambiguities in the derived Feynman axioms, and they are brought about in sharp relief by the Wigner's friend paradox, which was introduced by actually Hugh Everett in his long unpublished dissertation on the many worlds interpretation. But he was at Princeton with Wigner, and Wigner is more famous for describing it in a paper called Remarks on the Mind-Body Question in 1961. This thought experiment, again, highlights the ambiguities in the derived Feynman axioms that arise when you have large systems. So in this thought experiment, we've got W is Wigner. Wigner remains outside a box that is sealed sufficiently well for the duration of the experiment. We can treat it effectively as perfectly sealed. And Wigner's friend is inside the box and does a measurement process on a quantum system that is also inside the box. Some people ask, is this the same as the Schrodinger cat experiment with the cat doing the measurement on the radioactive atom? In a sense, yes, if the cat can talk. Wigner's friend is a talking cat if you want. Well, we have an ambiguity now. We have an ambiguity. We have 2 observers. Very important, we have 2 observers. One does a measurement inside a sealed box, one does not. And now the question is, do we activate the collapse axiom or not? And in fact, there's just not an answer. The axioms don't render an answer here. And you might say, well,
that doesn't sound right to me, because the axioms didn't refer to an observer, did they? Go back to the axioms. Did they refer to an
yes,
observer?
that's true. But the axioms did refer to a measurement.
So the real question is not where the observer is, it's where the measurement is.
Yes, that's right. Yes, right. Good. Fair point. Good. Okay. So yes, that's right. Yeah. So in the original, with it, Everett formulated it, he talked specifically about observers, and he talked about a measurement done by the person inside, and then possibly a later measurement done on the outside. But fair point. That's actually immaterial to the question. The question is, if a measurement was or was not done inside the box, what do? Do we collapse or do we not collapse? And the axioms would say we do.
Exactly. They're
axioms
not ambiguous. There's no ambiguous.
The way I formulated them, there are other ways to formulate them when we talk about observers having. Fair enough. The axioms are ambiguous. Fair, if that's your point of view. Okay. Okay. But this leads directly to the measurement problem. So what precisely counts as a measurement? What is the magical thing that Wigner's friend did in the box that magically made this axiom happen? When do measurements among interactions have this unique property? They trigger collapses to apparently unique outcomes. And there's another problem that's, I think, not widely discussed. I call it the category problem. Measurements are a seemingly very narrow category of physical phenomena. There appear to be things that are not measurements that are also going on. How do we account for all those things that are not measurements that appear to be going on in the world around us? Now, you could take various views on this. You could take the view that everything going on is in fact a measurement, or most of those things are measurements. Or you could take the view that we don't need to worry about things that are not measurements, because at the end of the day, we only know about those things by doing a measurement. There's a whole variety of things you can say about this. Nonetheless, as an intellectual problem, it'd be very nice if we could make some progress in that question as well. At the very least, we'd like to be able to tell people working in early universe cosmology that when they talk about gases mixing in the early universe, because there were gases mixing in the early universe, even though there were no observers doing direct Feynman measurements on them. All right, I like to write out the Wigner's friend thought experiment as a flowchart, just to keep everybody clear and honest. Because when I talk about the Wigner's friend thought experiment, people tend to sort of swerve and weave, and sometimes wave their hands. Let's just get everybody totally honest. Okay. So here's the Wigner's friend flowchart. I call it the Wigner's friend flowchart. Question: does the overall quantum state in fact collapse due to the measurement done by the friend inside the box, which we said was a measurement process somehow? Do we think the overall quantum state actually collapses? Okay, and so we have 2 possibilities, yes or no. You could take yes, but it collapses. We apply that axiom, it collapses. And now we have another question. Did it collapse because of the friend's measurement? Well, if it did, we're going to run into the measurement problem and the category problem and all that we just talked about, what counts as a measurement, what doesn't, and so forth. And we, for 100 years, have not been able to settle on a nice rigorous definition of what a measurement is and when to apply that axiom. Okay, well, maybe it collapsed, but it was not due to the friend's measurement. Something else made it collapse. And now you're in a context of theories known as dynamical collapse theories. There's a whole host of them, and they have all kinds of different mechanisms for what could have caused the collapse. And this is a family of approaches to quantum theory. Some of them have been ruled out already. But there's just some interesting work going on in that field. All right, you could take the view the overall quantum state does not collapse. Maybe you take no in this chart. Well, did the friend inside the box nevertheless obtain a definite unique measurement outcome despite the fact that it is not reflected somehow in the overall quantum state? If the answer is yes, that despite the fact that the overall quantum state does not collapse, there is also a definite result, then we are manifestly saying the quantum state is giving us incomplete information, and so we are in the realm of a hidden or physical variables theory. If we say no, Wigner's friend did not obtain a unique outcome, we still have two possible answers. One is, were there any measurement outcomes at all? If yes, then we have something like many worlds or many versions of Wigner's friend or something like that. We'll run into certain fundamental problems with this approach that I may or may not have to talk about in the main talk. We could talk about Q&A, probabilities and so forth. If we say that there were no measurement outcomes at all, then we're embracing a kind of anti-realism. And this can be, this is a self-undermining thesis, because if there was in fact no result of the measurement, any of us could be Wigner's friend. And if none of us are doing measurements, then the whole scientific enterprise did trouble making sense of it. Okay, so this is your chart, and you should pick where you live on this chart. For this talk, I'm picking this box. This is the box I'm picking. I think this is the most promising box, and I'll explain why.
Which box? The yellow one.
The yellow one, I'm sorry, there should be a yellow bar around it, sorry. I just realized now that if anyone's having trouble seeing that, it's this box. It's the box in the middle, sort of on the right. Okay, good, thank you. Yes, I should have had like an arrow or something, but the diagram was already a little busy, and I didn't know if I could fit anything else into this diagram. Okay. So here's some implications of the measurement problem, okay? So, well, I mean, for tabletop and accelerator physics, you know, where you're smashing together small particles or you're dealing with atoms and so forth, you can usually ignore the measurement problem for practical purposes. I'm gonna say right now, like, if you are practically minded and all you want to do is smash particles together or do manipulate cold atoms or cold molecules, I don't think you really have to worry with the measurement problem. You're fine, and if you want, you can ignore the rest of this talk, maybe. In that case, you can just regard the textbook quantum theory as an instrumentalist theory, just a mathematical tool set for making predictions of measurements. You can just, as David Mervyn said in his 1989 article in Physics Today, "What's Wrong with This Pillow?" It's a strangely named article. You just shut up and calculate. Okay. But when you're working in astrophysics, at least in parts of astrophysics where you care about like large-scale quantum effects or quantum gravity or early universe cosmology or quantum cosmology, you run into situations in which you find yourself asking whether we can apply quantum theory to large objects, and also in scenarios, maybe in fictitious universes with different laws of physics in which there don't appear to be any measuring devices or observers anywhere. And I read a lot. I mean, I read a lot of papers in high energy theory, and I do sometimes come across papers by serious people who run headfirst into these ambiguities, and they just pick a direction, seemingly on intuition or something like that. And that's just a problem. It's an ambiguity, right? How do you know when to invoke the measurement axioms in these scenarios? Okay, so I like to stack up the measurement problem against the black hole information loss problem. Why? Because the black hole information loss problem is considered a very important problem by some people in physics. I think it's an important problem. I'm not going to dispute that. But it's interesting to compare it with the measurement problem. So they're both decades old. Measurement problem's older. They both seem to involve a breakdown potentially of unitary evolution. The measurement problem is hard to study empirically because exactly when those ambiguities show up, it's for big systems. And big systems, the discrepancies between the two ambiguous choices of what to do are very small and very difficult to measure. However, the black hole information loss problem is even harder to measure experimentally. We can talk about like what you'd have to do to actually experimentally verify whether black hole evaporation is unitary or not. But it is definitely a much harder problem than the measurement problem. The measurement problem affects a theory that may be part of quantum gravity. I mean, the black hole information problem does as well. They both are part of, presumably, a theory of quantum gravity. They both generated wild metaphysical speculations. I think that's fair to say. They both keep producing interesting spin-offs. That's one good reason to work on them. Measurement problem has generated a Nobel Prize. None yet for the black-hole information loss problem, but maybe, just wait, maybe someone in this room. Okay, I want to say a little bit about the category problem now, because it's a problem you might not have heard of before. So I said the category problem is how we go from the narrow phenomena, the narrow category of measurement phenomena, specifically to like the broader set of phenomena that happen. But you can phrase this in a different way. On the one hand, you can think of happening averages, like if you're studying Brownian motion or you're studying the typical behavior of organisms in some large collection of organisms, and we can't track everybody, so we just sort of, on average, say what they're doing. Then we're talking about a happening average. Stuff is happening, and we're just going to coarse-grain our average, and so we'll say on average what's happening. On the other hand, the direct line axioms don't give you those kinds of averages. They only give you measurement outcome averages. The so-called quantum theoretic expectation values. Right, they're very clear on this. When you put brackets around an observable in quantum theory, what we're saying is that quantity is the thing. It's a statistically weighted average of measurement outcomes, numerical measurement outcomes, weighted by their measurement outcome probabilities, and that's it. There's specifically one kind of average, and just because they're both in brackets doesn't mean they're both the same kind of average. In other words, yes, I just said this, because these two quantities are both in brackets and may sometimes have approximately the same numerical value for certain choices of the symbol x, that doesn't mean they're physically the same categorical kind of thing. It's like saying that there's like 10 different kinds of entropy, and in some situations, conceptually different kinds of entropy are numerically the same. It doesn't mean that they are, therefore, the same thing. And yet this elision between the two kinds of averages is implicit and pervasive in textbooks in the research literature from condensed matter physics to quantum gravity. How do you know Ramamurti Shankar's book, Principles of Quantum Mechanics, that beautiful big pink book on quantum mechanics? His whole chapter 6, called The Classical Limit, is built on this fallacious identity between these two kinds of averages. But when you pick up papers in like semi-classical quantum gravity, you know, where you take the Einstein field equation and you take the stress energy tensor and you just put brackets around it, like that's the wrong kind of average. It's not the kind of average you want to do for general relativity. So this is like a pervasive thing, and I'm not saying it's wrong to do these things, but if you're going to do them, there should be a better argument for them. The argument doesn't seem to come out of the direct line axioms unless you can solve the category problem. So quantum theoretic expectation values with quantities like correlation functions and functional integrals are often talked about as if they're averages of phenomena really happening, and that's hard to square with the axioms. Now you might say, wait a second. You're saying that the stuff about quantum theory is not about stuff happening, only measurements. But there's stuff happening in quantum theory. There's the Hilbert-space objects. There's wave functions, density matrices, and they're evolving in time. Can't we say that the physical stuff is them? Can't we say that like a wave function is a physical object and that's the stuff that's happening? Can't we assign phenomenal physical meaning directly to the degree it's in Hilbert-space? Well, there's a problem. So quantum theory has a little-known form of gauge invariance. I've given this talk many times, and not a lot of people seem to know about this. Occasionally, people will know this for sort of random reasons. I don't quite know why. So let V of t be any time-dependent unitary operator. The time dependence is key. This is not a constant unitary operator. It's time-dependent. Then you can do the following gauge transformation, which you can show leaves all empirical predictions of quantum theory exactly invariant. I mean, it's just what you do with a unitary operator. You just multiply everything. You multiply your state vectors by it. You sandwich your density matrices and your observables by them. This is not the time evolution operator. It is an arbitrarily chosen time-dependent unitary. Totally arbitrary. That's the point. Now, if this were constant in time, then this would just be a unitary change basis. We all know that's not super interesting. This is time-dependent. You might go, well, the time-dependent unitaries, they're not really a symmetry. They're not a symmetry. They're a gauge invariance. If we transform all of our ingredients like this, and we transform our time evolution operators as correlators that correlate the time evolution at one time to another. In fiber bundle language, we're saying that time is a one-dimensional manifold, and we're imagining we're fibering the Hilbert space over this one-dimensional manifold. We're imagining we're doing independent unitary rotations on each fiber. And then the time evolution operator is the correlator between the different points on this fiber bundle. And the Hamiltonian, which is the generator, which it's exponentiated to get the unitary time evolution operator, it transforms in a very interesting way. Some of you may recognize this transformation law. This is a non-abelian, it transforms exactly like an n by n, where n is the dimension of the Hilbert space, non-abelian gauge potential. So the Hamiltonian is in fact not an observable quantum theory. It's not gauge invariant, although in some choices of gauge, it's equal to like p squared over 2m plus v. That's the gauge invariant observable. But the Hamiltonian's value can vary depending on what gauge you're working in. And this was first noticed by a philosopher, Harvey Brown, in 1999, in a paper called aspects of objectivity in quantum mechanics. What a philosophy sounding name that is. But it was actually a very concrete problem, how to think about non-Galilean transformations from inertial to non-inertial reference frames in quantum mechanics. Good, right. I should also just point out that the way the density matrices transform does not commute with partial traces. So this leads to some very interesting ambiguities that arise when you're studying systems with many subsystems in a relativistic context. The whole thing becomes kind of a mess. So basically what this is telling us is that all these Hilbert-space ingredients are gauge dependent. Their physical meaning, like all gauge variables, is suspect. Indeed, you can map any state vector trajectory in the Hilbert space to any other state vector trajectory. A state vector trajectory therefore contains no gauge invariant physical content. Well, then what is gauge invariant in textbook quantum theory? Well, sad to say, it's the measurement outcomes, measurement outcome probabilities, and the expectation values. And if that's all that's gauge invariant, we're right back into the category problem. So like, you could think about these things really carefully and keep looking for ways out, but it's just really hard.
That's also true in GR, right? The only gauge invariant things are dimensionless scalars, right, that come out. So these are kind of the analogs of the dimensionless scalars in GR.
In a way, but like there are a lot of things in GR that are gauge invariant and like have a real like meaning, like the number of times two world lines intersect, for example, even if neither of them are observers. That's a thing that has a diffeomorphism invariant meaning in GR.
Good.
Like GR is certainly sparser than you might think. A lot of the things that you might think are the physical ingredients of GR turn out to be gauge dependent, but there's a tremendous amount of gauge invariant content with clear physical meaning in GR. That's observer independent. That's key. All right, so I want to say a little bit about weirdness versus brokenness, because people say, well, what's about quantum mechanics is weird. It's just weird. You're so prejudiced. You don't like weird things. You don't like weird people. You're awful. Okay. So the measurement problem, the category problem are not issues of weirdness or unintuitiveness. I like weirdness. I'm weird. Ask anyone who knows me. Okay. I like weird people. Weirdness is fine. Unintuitive. I'm very unintuitive. Time dilation, breakdown of simultaneity, super weird. Gyroscopes, black holes, weird. Superconductivity, superfluidity, weird. Magnetic monopoles, weird. Extra dimensions, weird. No. The issue with the textbook formulation of quantum theory is that although it works well in many circumstances, it is just broken in certain circumstances. It is at best an effective theory. And we shouldn't pretend otherwise. We shouldn't tell students that there aren't serious problems. We shouldn't claim that decoherence can solve the problem. We shouldn't put off fixing the theory any longer. Let's just go about fixing it. You may be saying to yourself, do I really need, Jacob, another interpretation formulation? What are you going to do with the rest of your time? Don't we already have too many interpretations as it is that claim to solve the measurement problem and the category problem? Well, I'm going to argue that we don't have any that meet all of a very minimal set of consistency requirements. These are not aesthetic requirements. They're not things that I just like. They're not about, oh, I like my physics a certain way, right? I'm happy to discuss all of these and why the other approaches have trouble with them in the Q&A if you want. One is just empirical adequacy, which just means the theory should make the right predictions experimentally. The things we observe, it should be able to handle like the theories we have that make good predictions. It should be able to handle that. And there's some problems with Bohmian mechanics and then Mendel's interpretation in this regard. I've talked to some of you about some of these problems, and if you want to talk more about it, you can come find me. We can talk in the Q&A. There isn't time to talk about these things in this talk. We want the theory to make unambiguous predictions for large systems when you treat them quantum mechanically. We don't want to run into this ambiguity that we had. We want to be able to account at least schematically, not detailed, but schematically for how macroscopic systems and classical things are supposed to emerge without running into the category problem. And this is the problem for the Draconian axioms, also a problem for the Copenhagen interpretation, which has a somewhat more precise definition depending on whom you ask. And we also like, if possible, to avoid an endless list of extra empirical assumptions and speculative metaphysical hypotheses. The acronym here is very intentional. And I'll talk, if you want in the Q&A, we can talk about why this is a problem for the many-rules interpretation. Now, you may be saying to yourself, wait. What about this explanation? Maybe you took a class once where the instructor presented a crisp argument why textbook quantum theory was just fine. Maybe it was a lecture you saw or a book you once read. You can't quite remember, but you know you read it somewhere. Maybe it was Niels Bohr or Sidney Coleman or Zurek or Nima Kani-Hamed or Julian Schwinger or Asher Perez. Surely I've read or seen one of these arguments before. I've seen all of them, just so you know. And so I'll tell you is here's a homework exercise for you. And it's a homework exercise that people have done and is often very elucidating. In fact, just as a brief story, we have a historian of physics, Peter Gallison at Harvard, and he had a long friendship with Roy Glauber. Roy Glauber is a Nobel Prize winning theoretical physicist, an AMO theoretical physicist, won the Nobel Prize for his work on coherent states and lasers, the theory behind lasers. Roy used to say, quantum mechanics is fine, no problem. And Peter would say, if you have like an hour, could you just sit down and explain to me, like maybe just write it up? And Lover says, oh, sure. I did like not an hour, half an hour. Just need to sit down for half an hour. I'm just so busy. I don't have time to do it. And so every time Peter would see, I got this sort of directly from Peter. Every time Peter would see it, he would ask Roy, so if you had a half hour to write this down, and Roy was like, oh, I'm sorry, I've been super busy, I forgot. Next time. And then one day, Roy comes and finds Peter, and he just sort of like sheepishly comes over and says, I think there's actually a problem here. So here's the homework exercise. All right, write down your argument in full. Write it down. Start from the axioms, whatever Dirac von Neumann axioms, if that's what you're claiming is the good axioms, whatever axioms you want. You got to fill in all the details. You can't just wave your hands. Like, you can't just say, and then magic happens. Like, give me the full argument in detail so we can really evaluate it. And if you think you've succeeded, come please chat with me. I'd love to talk to you. Maybe you have. That'd be great. I'd love to talk to you. But a word of warning, not as straightforward as you might have been led to believe. And I have seen many such arguments. The history of quantum foundations is a veritable minefield of plausible sounding but unsuccessful such attempts that go by many names that I won't have a chance to talk about. So I'm going to talk about one of those approaches. This is the one that I'm currently working on. So what are the goals of this talk? I'm going to argue that every quantum system, if you so choose, could be understood as a certain kind of stochastic process, a recently characterized class of processes called indivisible processes. And in this picture, there is no fundamental role for wave functions or density matrices. They are mere mathematics. They are non-physical. Additional goals. I'll define what an indivisible stochastic process is. I will give a precise correspondence between indivisible stochastic processes and quantum systems as described in the Hilbert-space picture, with potential applications outside of quantum physics to stochastic modeling. I'll describe some concrete examples. Some of these I don't have time to discuss in the talk, so if you want to talk about it, we'll talk in the Q&A. In the process, we'll demystify and deflate some of the exotic features of quantum theory. I'll be able to talk about like what interference is, or at least one way to think about what interference is, rather than just saying it's math and it does stuff. And at the end, I'm going to introduce and this is where you get to physical philosophy, a new way to think about causal influences, and then I'll talk about Bell's theorem and why it challenges some of the things that Bell says. Okay. So as motivation, let's revisit the double slit. Yes?
Quick question. Did you ever give us that set of like minimum requirements that interpretation must satisfy?
Yes, that was on the slide where I listed empirical adequacy and I listed no ambiguity for large systems and a schematic classical limit and no speculative metaphor. Yeah, but no long list of speculative metaphor hypotheses. Happy to go back if you'd like.
No.
Okay, we're good. So let's revisit the double slit experiment. I have to put this in because anytime I don't mention this, people say, what about the double slit experiment? I'm going to do the double slit experiment. I'm sorry, I have to do this. This is like you open up the beginning of volume 3 of Feynman's Lectures in Physics, where he presents the double slit experiment and says it contains really the only mystery of quantum mechanics. Let's talk about it. So just to be clear, this formulation I'm going to tell you is very general. It's not about any particular kind of quantum system. You can apply it to any quantum system you want. But let's do a familiar single particle example just to give a good motivating example. So if we know the double slit experiment, you imagine sending particles one at a time, always emphasize this, one at a time, toward a wall with 2 slits, and then you observe where the particle arrives on the screen. And they say one at a time because, well, they don't want you to think maybe the particles are bumping into each other, but that's actually not the reason they're sending them one at a time. The reason they're sending them one at a time is because if you send them one at a time, then the wave function has as its domain 3-dimensional space, which makes it look like these are waves that move in 3-dimensional space, and they go through holes and they interfere, and it's very intuitive, and it gives us a nice intuitive way of understanding it. If you did 2 particles, the wave function's domain would be 6-dimensional configuration space. If you have n particles, it would be 3 n-dimensional configuration space. Good luck providing that as an intuitive explanation of the interference pattern that you get. It sends students, I think, the message that I think everyone who uses quantum mechanics daily knows, but students often don't know, and certainly you don't get this sense from reading Griffiths for most of it, that wave functions don't live in physical space. If you've got 3 particles, their domain is 9-dimensional space. And you get into this habit when you're first learning quantum mechanics, you think of wave functions as like almost like electric or magnetic waves, but they're really something altogether different. Anyway, okay, so here's the experiment. 2 slits close together. Let's let A denote in very generic terms starting conditions, B which slit the particle goes through, C where it lands. So you do this experiment. You make a certain assumption. This is the classical assumption. This is usually made only implicitly. If you're assuming Newtonian dynamics, then you're implicitly making this assumption. You could be a little more general than Newtonian dynamics. You could let the dynamics be probabilistic. The assumption is that the conditional probability of the system being in hole B, given that it was in initial conditions A, multiplied by the conditional probability that it was in hole B, that it ends up at spot C on the screen, given that it was in hole B. You multiply them together, you sum on B, which hole, And this is supposed to give you the conditional probability of where it ends up on the screen C, given the initial conditions A. A deterministic Newtonian type system trivially satisfies this without probabilities. Okay. Now, this assumption doesn't follow from the general rules of marginalization. It entails a certain implicit assumption. It requires a Markov assumption. And it turns out this Markov assumption is related to a notion called divisibility that I'll talk about a little bit later, which is the antithesis of indivisibility. We had to assume that we had good laws that take us from A to B and from B to C, and that they can be concatenated in just this way to give us that probability. But this is not a general fact about how probability works. It requires certain assumptions about the laws of physics. Now, if you do make this assumption, you predict the following pattern. You get dots that look kind of like this. This is a two-dimensional projection of what you see. And it's really the merging of two sort of normal distributions from the two holes. They blend together, you get this sort of picture. And this is indeed what we see for macroscopic objects like stones. Now, if you do this experiment for electrons, again, one at a time, supports one at a time, you observe dots that look like this. Okay. Now, these dots, once you've done this experiment like 10,000 times, you see this pattern. The pattern, if you sort of plot the histogram, looks like this. It's important you don't see a wave in any one run of the experiment, but over many, you get what looks kind of like this wave-like interference pattern. The question is, does this mean that each particle is therefore a Schrodinger wave, or that each particle somehow goes through both slits? Not necessarily. What I'm going to show is that if you drop the Markov assumption, then generically you get exactly these interference effects. And we'll talk about that in detail as we go, but this is important just to be aware, like I know the double slit experiment, we are going to account for it. And what that works. So what is an indivisible stochastic process? What is the basic idea behind this talk? An indivisible stochastic process is a kind of stochastic process. Stochastic just means, it comes from the Greek word stokos, was apparently the stick that archers used to do target practice with. So this connection between like probabilisticness and like arrows is apparently a very old vintage. So stochastic came to mean aim or guess, and stochastic is like probabilistic, but usually with a more dynamical feeling, like it's something that's happening in a probabilistic way, dynamically. Now a Markov process we just talked about, a Markov process is one where at every moment you have a probabilistic law that tells you how to get to the next moment. You can to daisy chain or concatenate these laws together. A non-Markovian process is more complicated. An indivisible stochastic process is a particular kind of non-Markovian process, but it's very rudimentary. So rudimentary, it's even simpler than a Markov process. And I know people who work in like biostatistics and statistical modeling, and this is new to them. I haven't met anyone who's encountered these before, and all of the people I've spoken to have said this is actually interesting, but they just didn't realize you could do this. But yes, you could do it, and they have useful applications. So what is an indivisible stochastic process? Here are the fixed ingredients. So it's a stochastic process, so you run it. And the question is which ingredients are the same in every run and which ingredients are allowed to be different from run to run. Here are the fixed ingredients. Here are, if you will, the axioms. The kinematical axiom, like what the thing is, it's a thing with configurations that you can assemble into a configuration space. Very much like you'd think classically. So configurations, if you want to study a system of particles, it would be arrangements of particles in space. If it's a system of fields, it would be field intensities in physical space. And we call that configuration space C. That's pretty much what we do classically. The dynamics is going to consist of a very rudimentary set of conditional probabilities that relate configurations at pairs of times. That's it. So this is called the conditional probability map. That's the Greek letter gamma, capital Greek letter gamma. And it's a map that probabilistic tells you what the probabilities are given where the configuration of the system was in at time t naught, what configurations will be time t. Now, these are sparse. They're not given for all possible pairs of times. They're given for sometimes. And you might ask yourself, when does that ever happen? It happens a lot. Once you start looking for indivisible systems, you begin to find them everywhere. It happens in epidemiological studies where you give certain drugs to certain subgroups of people, but you don't give second drugs to people who had first. Like there's situations which you just don't naturally learn more than just a very sparse set of first order conditional probabilities. And there are other situations in which these things may also arise. Are they useful? Well, that's kind of the point. So the set of times you can condition on are called division events for reasons that I'll explain later. That's it. Those are the fixed ingredients. And then there are contingent ingredients, the things that differ from one run to run. One thing that differs is just which particular trajectory the system took, but we don't necessarily know what that is. And also there is a probability distribution, P of t. This is just the distribution, the probability the system is in, which of its configurations at the time t, and this changes with time. Okay, so these are the axioms. There is a linear marginalization rule. Given the standalone probabilities at time t naught, You take the conditional probability map, it gives you conditional probabilities that linearly take you from the standalone probabilities at T naught and give you the standalone probabilities at T. And this is linear from the definition of how old-fashioned probabilities work. This isn't some magical, this is what I mean, but this is how conditional probabilities, this is the law of total probability. The fact that this is linear will be important later. This is a linear rule. It's very important that it's a linear rule. I've painted gamma in brown because it's law-like. Okay, that's it. That's it. Those are the axioms. That's it. We're going to see how far we can take this now. So let me say a little bit about indivisibility. So it's a simple, remarkably new idea. Think of it as a failure of iterativeness because we only have this sort of sparse set of pairwise conditional probabilities. We can't necessarily daisy chain them together. We don't get a Markov process. But when you start looking for them, you find them everywhere. And if we see them all over the place, why can't quantum systems do that? That's basically the argument we're making. The idea of indivisibility actually originated not in the classical theory of stochastic processes, but in the theory of quantum channels. In a paper called Dividing Quantum Channels that was published in Communications Mathematical Physics in 2008 by Mikhail Wolf and Ignacio Chirac, based on a 2006 preprint. It was only first applied to classical, ordinary, old-fashioned probability theory in 2020 in a preprint that it was ultimately published in 2021 by Simon, Mills, and Kevin Modi, who also work in quantum information. And they mentioned it as an offhand remark in Figure 6 on page 15 of their paper. Which was a beautiful review article on stochastic processes both in quantum mechanics and classical mechanics. They noted it and then didn't do anything with it. They just noted, oh, that's a thing you could do, but who knows what it's good for. I know this because I've talked to both of them and they didn't realize you could do anything with these things. All right, so what is indivisibility? It's just this breakdown, and I'm just rephrasing now in mathematical terms what I said. Even if you're given the conditional probabilities to go from T naught to sometime T prime and from T naught to T, you're not necessarily given that purple matrix in between that you can just daisy chain together to get from the intermediate time T prime to T. That is, we cannot divide the time for this law into smaller subintervals of time. This is not to say that time is discrete. T here can be any time you want. It's just that we may not have laws that connect all possible times. That's the failure of divisibility. And there are explicit cases where you can prove that no purple matrix exists. You can verify that if you try to write it down, it would have to have negative entries or things that don't make any sense. Now, for a textbook number, yes.
So if I ask, like, what's the probability of going from, the purple thing, T prime to T? What's the probability? Like, what's the answer?
That's an excellent question. Let's talk about it in the Q&A, because there's like a subtle way to answer that question, but it'll take me a little bit too far. For now, so I say there isn't one that concatenates this, but when you like numerically simulate this, you will get things that look like conditional probabilities numerically, but they just don't satisfy this law. So it's just more, I'll explain it later, but there's a lot of subtlety here which we can talk about. So it's a good question. All right, so now you might ask, why didn't the people working in the stochastic processes know about this stuff? I mean, did they know about non-Markovian processes? They did, but non-Markovian processes usually require specifying a lot more data than what we've supplied. I've only supplied like a sparse set of first order conditional probabilities. Usually when people think of a non-Markovian process, they're thinking that you specify joint probability distributions over everything and over all times. And these get extremely complicated. There's a tremendous amount of data that you need. And like, it's hard to do anything with them because you have to specify an infinite amount of data to actually get anything going. And I can say a little bit about work that's being done to use quantum simulation to get at these systems, but that maybe the Q&A. In a Markov process, we're not throwing away all those higher order probabilities. This is key. In a Markov process, we're assuming that you have joint probabilities over everything. We're just assuming that they trivialize. They're numerically equal to first order ones, so we only have to focus on the first order ones. In an indivisible process, we don't even have the higher order ones. It's not that they exist and are equal to something. We're just not specifying them at all. So these models are actually very simple, so simple that they weren't noticed. That said, when you actually simulate these systems on like a computer, which you can do on Python code if you want, you find that they're non-Markovian at infinite order. It's just that all those higher order probabilities are not fixed from one run to run. And again, these models show up in lots of examples, epidemiology, neuroscience, whenever we lack enough information about conditional information. So they're really out there in the world. Why can't quantum systems do that? So I'm going to give a concrete example here. Consider the simplest kind of discrete time deterministic process you can imagine. I'm going to move a little quickly through this. So imagine you've got a totally boring deterministic process. It's got n configurations and it transitions in time steps delta t by a simple permutation, not necessarily even time reversal invariant. So you know, 1, 7, 3, 2, 30, it's just some sequence, and eventually it repeats because there's finitely many and it's deterministic. We eventually have to come back. And permutation matrix has to come back. We can represent the system using a vector space language if we want. We can identify each of the configurations with a standard basis vector. And then we can represent the dynamical laws as the action of a permutation matrix, repeatedly acting on the system. So with a suitable permutation matrix, you just repeatedly act and you generate the entire dynamical process. Now, sigma here is an n by n permutation matrix. Every permutation matrix is also a unitary matrix. In fact, just as an aside, the fact that when you do it n times, you get the trivial identity matrix means its eigenvalues are all nth roots of unity, which is fun. For t, any smoothly variable time, let t be any smooth time parameter, not limited to the discrete time steps, we can take the roots of sigma, we can take to the power t over delta t, it's a irrational root. So sigma to an irrational number root. And because we started with a unitary matrix, the result is still going to be a unitary matrix. Powers of unitary matrices are still unitary. If I now take the individual entries of this unitary matrix, entry by entry, and mod square them, by construction, I get a matrix, and also an n by n matrix, whose entries are non-negative and whose columns sum to 1. That is by definition a stochastic matrix. But by definition, by construction, this is not just a stochastic matrix, but a unistochastic matrix. A unistochastic matrix is, by definition, a stochastic matrix whose entries are the mod squares of the entries of a unitary matrix. These were first characterized by mathematician Alfred Horn in 1954. They were given their modern name by Robert Thomson in a lecture at Johns Hopkins in 1989. I have never been able to find a lecture. If any of you find a lecture, please let me know. Yes.
Generically, it's very non-unique because you're taking the power of like some fundamental power.
Yep.
So are you saying you can choose any U or?
There will be many to oneness in all directions here. Yep.
Okay.
We're not looking for a unique correspondence. Yep. Good. So anyway, so this defines an indivisible stochastic process because it defines exactly the set of quantities that we use to define our process. And this indivisible stochastic process analytically interpolates the original discrete time deterministic process to a smooth and time indivisible stochastic process with a property that whenever you hit an integer number of time steps, you return to this permutation matrix. So it interpolates the process smoothly. Using this unitary matrix, we now have this unitary matrix. We can take u from 0 to t and u from 0 to t prime adjoint. We can multiply them together and define a purple matrix that I'll call u from t prime to t. And by construction, this matrix now satisfies a composition law. Oh, isn't that a beautiful composition law? Nice composition law. 0 to t prime to t is equal to 0 to t. That's great. I thought you said we couldn't do that. Well, we can't. You see, the relationship between u and gamma is an entry by entry modulus squaring, which means the fact that this holds for u means that it does not hold for gamma. The purple matrix that you get from squaring the entries of u give you a purple matrix gamma that does not satisfy this condition. If you attempt to do it anyway and like write this down, just mod square the entries of u and pretend. Think of this as the least squares approximation in some metaphorical sense to a Markov process, to a divisible process. You'll find that the discrepancy between the correct evolution, exemplified by this brown gamma, and the wrong evolution, given this Markov process, you'll find that the difference is exactly the formula for quantum mechanical interference. Like, it's literally the same formula. And so this gives a really interesting way to think about interference. Interference is not some abstract thing that just indirectly produces weird measurement results. It's literally measuring the difference between a process being divisible or roughly speaking Markovian and not Markovian or indivisible. So essentially, anytime you pretend the process is Markovian when it's not, and you get the wrong answer, the discrepancies are, conceptually speaking, of the same kind as the interference we get in quantum mechanics. However, the stochastic process that I've written down will divide at the special integer time steps. At those special integer time steps, when gamma reduces to sigma, then you'll get division, and we call these division events. This is our most rudimentary example of division events. Now we have u, and if u is a smooth function of time by construction, so we can take derivatives of it and define a generator. We can introduce, if we assume our initial condition was E1, and we started in configuration 1 and evolve it forward with u, this defines a complex valued n by 1 vector, which we'll call psi of t. Psi of t will obey the Schrodinger equation. The Born rule will come out where this is now the probability the system is literally in its ith configuration. This is not just a measurement probability anymore. More generally, if you don't know the initial configuration of the system, yes.
So you wrote down those gauge transformations at the beginning. Are the gammas gauge invariant?
Yes.
Okay.
Yes. In a way, and also not in a way that again we talked about in the Q&A.
Okay.
Yeah. Okay. It's a good question. So more generally, we don't know under that gauge. Yes, there are gauge invariant under that gauge invariance. But there is there's some many to oneness that we can talk about. Okay, so more generally, if we don't know the initial conditions with certainty, We represent our uncertainty with some initial probability distribution, P1 of 0 through Pn of 0. These are our initial probabilities that we associate to different possibilities. We can assemble them into a diagonal matrix rho of 0. We can now define a row of T by conjugation by U, and then the row satisfies the von Neumann equation. That is an actual commutator, not like this is not like a Louisville Poisson bracket type thing. It's a real commutator. The Born rule becomes this famous formula here, where Pi is an elementary projection matrix. This is all the usual stuff that we see. So that's a concrete example. Now let me lay out what the correspondence actually looks like in general. So that was a concrete example. Let's actually, like, what does it work more generally? There are two directions here. On the one hand, stochastic to quantum. How do we get from a stochastic process to a quantum process? So given any indivisible stochastic process with n configurations, so it's got a gamma matrix, introduce a not unique n by n matrix theta, and it's introduced by requiring that the mod squares of its individual entries are equal to the entries of gamma. This is not unique again. And this new matrix satisfies the following sum rule, which you can think of as a very generalized notion of unitarity. It's not unitary. You can define a time-evolving density matrix in exactly the same way we did in our example. Take the initial probabilities and put them on a diagonal matrix and sandwich them between theta and theta dagger. And you can already start doing some Hilbert-space stuff. And for shortness of time, I'm not going to show you that, but you can already start doing like Born rule and interesting things this way. But I'm going to skip right ahead and say, if gamma of T is unistochastic, if it is a matrix of the form such that there exists a unitary whose entries mod squared gives you back the entries of gamma, well, then we just assume theta is unitary. And we can now take everywhere you saw theta to be unitary, and now we're doing just familiar unitary quantum mechanics. But interestingly, and I think this was not noticed until I think I proved it. If you don't assume that gamma is already, and this is particularly interesting for people who don't work with quantum systems, they work with stochastic processes, they want to use quantum mechanics. If you don't assume gamma is already unistochastic, you can actually, and this is sort of a construction, don't worry with the details, you can construct Krauss operators from it, and then apply what's called the Stein-Spring dilation theorem. It's a 1950s theorem, use Stein-Spring, and on a bigger Hilbert space, get a unitarily evolving system that represents your original stochastic process. There is not a unique way to do this. Nonetheless, it gives you a unitary description on a slightly bigger Hilbert space that you can use to model your original system. You get an emergent quantum system in a Hilbert space representation, and then you can show that that linear marginalization rule that I made a big deal about earlier is responsible for the linearity of this equation here, which becomes the linearity of the Schrodinger equation, which otherwise is just a postulate with no explanation. Now, in addition to explaining, like, giving it a nice, cute reason to think we can explain where the linearity comes from, we also talk about where the complex numbers come from. So famously, quantum mechanics involves the complex numbers. Why? Well, for n bigger than 2, for systems with more than 2 configurations, an n by n unistochastic matrix will not generally be representable using an orthogonal matrix. For n equals 2, you can show that every unistochastic matrix is actually orthostochastic. You don't need unitary, you can just use a real orthogonal matrix. But when n is bigger than 2, you can't take advantage of this correspondence without the complex numbers. The complex numbers are needed to get the Hilbert space picture. So to exploit the stochastic quantum correspondence and get unitary evolution, the complex numbers or some algebraic construct isomorphic to them will be necessary. There's a paper a couple of years ago, Why Quantum Mechanics Need the Complex Numbers. They got a lot of press. It was like in Nature. There are a lot of problems with that paper. If you want to talk about that in the Q&A, we can talk about that. Or meet me afterward. But anyway, Hilbert spaces are fictions from this point of view. So we might as well put complex numbers and then take advantage of all the great mathematical tools we get when we do Hilbert spaces with complex numbers. Actually, and this is just sort of an aside, when you want to deal with systems that have a notion of time reversal, you need a complex conjugation operator. And students who are taking quantum mechanics often find this very mysterious. But from this point of view, they're just pieces of representation. You need an operator that complex conjugates it. So it's an involution. You act twice, you get 1, and it anticommutes with I. This is often very surprising to students who are like, why does anything not commute with I? I is a scalar. Then IK and IK generate a Clifford algebra called the pseudo-quaternions. This was first noticed by Ernst Stickelberg, like many things. He was the first to notice, in a beautiful pair of papers, the first of which was 1969. However, I don't know of any observables that are built using K. I do know they're built using I, but not using K, but maybe we're too narrow-minded, who knows? Okay, yes.
Just a few minutes left, so you can.
Yes, let me wrap up. Oh, shoot, okay, yes, okay. So this is just a rehash. If you have a density matrix, your density matrix, if it's rank 1, you can factorize it, show that it has a Schrodinger equation, the linearity, like I said before. In this picture, wave functions, the Schrodinger equation are secondary pieces of derived mathematics. They're not fundamental objects. And the whole point of the unitary Hilbert space formalism is to give us a divisible picture. You can also go the other way. If you're given a quantum system, you pick a convenient orthogonal basis like you would if you were doing a path integral, let's say. You mod square the entries of the unitary, you get a gamma, and we did this in our example before. And you end up with a stochastic process. Now you may worry that we're losing phase information by mod squaring. Actually, it doesn't matter. You can show that as long as you bring your measuring device into the system, model it the way that von Neumann did or Bohm did, you can show that even without the phases, you get all the right answers. In a way, if you want to model a quantum system using the Dirac-Von-Neumann axioms and not include an explicit measuring device, then one way to think about all those phases that you're holding on to is they are encoding information at the unseen measuring device. If you actually just model the whole thing as one big process, the phases don't matter. I'm not going to have time to go through the measuring process here. This is in the papers. We can also talk about it in the Q&A if you want. I'm going to skip this division event stuff. I want to get to Bell. So decoherence and so forth. Sorry, tangle it. All right, let's go to Bell. Okay. So you get a stochastic quantum correspondence. Again, we can talk about all this in the Q&A if you want. It's many to one in both directions. For a given quantum system, there may be many stochastic representations, and for a given stochastic theory, there could be many Hilbert-space representations, very much like the relationship between a Newtonian system and its Hamiltonian phase space formulation. Like any form of analytical mechanics, the Hilbert-space formulation is still very useful if you want to specify microphysical laws in a systematic manner, study dynamical symmetries, calculate predictions. You certainly want to use it. So the last part of the talk is on causal locality. And this is actually a very important slide because there's some conventional wisdom here. When people say Bell's theorem, they could mean several things, and people often take it to imply several things. One is that no-go theorems have simply ruled out hidden variables altogether. And in fact, this is what it says in the announcement of the 2022 Nobel Prize for Ospe, Clauser, and Zeilinger. That is not what Bell said. Or hidden variables are possible in principle. We don't like them because they would entail non-locality and non-local causation. So as long as we don't have them, then we're good. We don't have non-local causation. That is also not what Bell said. What Bell said is that quantum theory is unavoidably non-local and causally, or causally non-local with or without hidden variables. And so hidden variables are not actually dangerous because even without them, we have properties. These are all mutually inconsistent. And again, Bell, according to Bell himself, he was arguing for the third. Now, I'm not going to have time to go through this because we are just out of time. So we can maybe discuss this in the Q&A. If people have questions in the Q&A, let me just say in words what's going to happen here. So Bell's original theorem, the kind that you find described in chapter 12 of Griffiths, is based on his 1964 no-go theorem. It's called on the Einstein-Podolsky-Rosen paradox. And that's important because he was responding to the EPR paper. Have people read the original EPR paper? Very few people have actually read it. And if you pick up textbooks on it, they almost all get it wrong. Like you pick up Stephen Weinberg's book on lectures on quantum mechanics, he gets it wrong. You pick up history books. The EPR argument is subtle, but it's important to get it right. The EPR argument says that if Alice is an observer and Bob is an observer and they share an entangled pair of systems, then Alice, by choosing what basis she does her measurement in, can seemingly steer the collapse basis of Bob's system. This term steering was coined by Schrödinger almost immediately after. It's called quantum steering. But of course, Bob doesn't know which basis it's been steered to, and Bob can't use that information to predict the outcome without some additional information from Alice. So there's no signaling going on here. Nonetheless, the idea that Alice, by her choice of measurement, can steer the collapse basis, bothered EPR. They said that because Alice could, for example, steer it one way and ensure a definite result for position, or steer it the other way and ensure a definite result for momentum, even though Bob hadn't done the measurement, indicated that either Alice was generating those answers non-locally, superlocally, or the system had the answers beforehand. So what EPR aimed to establish was that you either had non-local causation or you had hidden variables, which is not the way people often think about it. And what Bell did was show that even with hidden variables, you still end up with a form of non-local causation. Bell was not trying to prove that hidden variables lead to non-local causation. Bell was trying to close a logical fork. Einstein, Podolsky, and Rosen had said you either have non-local causation or hidden variables, and Bell was trying to show that even with hidden variables, you could not escape non-local causation. And so Bell's conclusion was that non-local causation was just unavoidable. However, the EPR paper and Bell's 1964 paper both helped themselves to a particular theory of causation called interventionism, which works fantastically if you're doing medical testing, but it's not obviously the right kind of theory of causation you want when you're talking about how elementary particles interact with each other. And if you want to talk about local causality, you have to play the game. You can't back off and say, we're not going to talk about our theory of causation, because if you're not going to talk about your theory of causation, you don't get to cite local causality. Bell seemed at some level to be aware of this problem. So in 1975, he published a new version of his theorem, which very few physicists seem to be aware of. It was a paper called The Theory of Local Beables. And in this paper, he found a different principle of local causality, one that does not require a notion of agents doing measurements and interventions, which is the problem. This was a much more elegant argument, but it rested on a new principle that he was unable to justify. Today, we call this the Reichenbachian principle of common causes. And Bell probably didn't know about this. People who knew him have told me that he wasn't aware of this. But it's a very sensitive, delicate assumption about how probability is supposed to work. And we already have lots of counterexamples. So that's not so great. In 1990, he came around again with another theorem, another version of his theorem, with a third modified premise. And the problem with this third modified premise is that it interferes with what's called settings independence. So the upshot is that Bell was never able to settle on a definition of local causality that both made sense and was violated by quantum mechanics. He kept fishing around for them and was never satisfied that he ever found one. And today there are other alternative approaches to local causality. I have one that we can talk about in the Q&A, and there are others. I mean, Guido Bacigalupi is a philosopher of science. He has another version of local causality. Anyway, Bell's definition of what it meant to be local causal is, there's now increasing sense that it is not the canonical way to define it. And without that canonical definition of local causality, you are now open to questions like, okay, which theories that entail variables that are beyond or in place of the wave function satisfy some maybe more robust or more fundamental definition of local causality? And we can talk about how this approach satisfies what is arguably a more fundamental definition of local causality. So this is the end of my talk. Oops. I didn't get to my conclusion slide, but there are various applications. We can talk about this also in Q&A. So let me stop there and take questions. Thank you. There's really a lot to say here. I mean, this is an ambitious thing, and if you want to work on it, come talk with me. Hard to fit this in an hour, I'm sorry, but yes, I'm happy to stick around and answer questions for arbitrary amounts of time. Yes.
Stochastic formalism that you were talking about, is this related to classical stochastic GR?
So tell me about classical stochastic GR.
Apparently, the goal of classical stochastic GR is to have a formalism of a GR that does not conflict with quantum mechanics. Since quantum mechanics are not completely deterministic, the GR is deterministic. And I'm not familiar with it, but my understanding of classical GR is it is a classical theory, it is not a quantum theory, and yes, it does not conflict with the non-deterministic aspect of quantum mechanics.
So what I'll say is I'm familiar with approaches that take classical general relativity and add noise terms, add small perturbed noise terms. Those are interesting, and there isn't necessarily a connection. Those noise terms are often taken to be Markov noise terms. So they're not of the kinds of stochastic dynamics that we're interested in here, but a very interesting and, as far as I can tell, open research questions. And I guess for historical reasons, it makes sense that no one did this. I mean, GR was basically done in 1915. Einstein field equation was published in 1915. The Schwarzschild solution was 1916. By the time people are already working on quantum gravity by like the late 1920s or 1930s, something like that. Pauli was already working on this stuff. The formal axiomatic theory of probability comes with Kolmogorov in 1933. And a robust theory of stochastic processes, not Markov's just Markov matrix, but like a full robust theory of stochastic processes in like the 1950s and 60s. GR was already old hat by this point. It makes sense that no one ever seems to have sat down and asked, can we build a fully probabilistic version of general relativity? Like, we're trying to do quantum gravity, which is great, but maybe we should do probability gravity first, stochastic gravity, like fully, not small noise terms, but like, is there a way to do general relativity with a fluctuating metric, fully stochastically fluctuating metric, without worrying about quantum theory? And it's interesting that, as far as I can tell, nobody has done this. It seems like an easier problem than quantum gravity, although I'm not sure. But my conjecture is that, and this is now just speculating, that if we could build such a theory, it would tell us something important about quantum gravity. Certainly, it would make sense to try to do it before we try to build quantum gravity. But again, for historical reasons, it makes sense that people didn't try. As far as I know, no one has done it. So that there have been various attempts to merge quantum theory and probability in various ways. Yes?
Could a major problem with quantum theory as it's presented be simply the view that everything has a wave function? If you say instead that objects are not a wave function, but a probability distribution over wave functions or a density matrix, and that the Born rule comes into play whenever entropy is able to increase. Entropy is part of the density matrix after all. A lot of the problems just go away.
I guess my question would be, I'd have to see in more detail how all the problems go away.
Okay,
There is not going to be an answer to the problems of quantum theory that one can state in one sentence. It's going to require doing a lot of homework and actually fit. So remember I said on a way earlier slide, if you think there's a way to solve the problems of quantum theory, what you owe me as a homework exercise is a detailed write-up where you fill in all of the gaps. And until I see that, I'm going to be very skeptical. I'm going to put on my analytic philosopher hat and subject that claim to scrutiny.
I'd be happy to talk with you about more details of it.
Sure. Other questions? Yes.
I have two like very basic questions. Okay. What was the stochastic matrix again? Was it the gamma?
So good question.
Okay.
At the heart of every indivisible stochastic process are these probabilistic laws that connect times. They form a matrix, and that matrix is a stochastic matrix, meaning an n by n matrix with non-negative entries whose columns each sum to 1 because each column represents a probability distribution. A unistochastic matrix is a kind of stochastic matrix. It was first characterized in the real analysis literature by Alfred Horn, a mathematician in 1954. I mentioned that. They have interesting analytic properties, well, just from a mathematical point of view. By definition, a stochastic matrix is unistochastic if there is a unitary matrix whose entries, when you mod square them, give you back the original matrix. Think of it almost like when we say a force is conservative, that means there's a potential whose gradient is the force. And that potential is not unique, but often way more useful to use than forces. Many problems you want to use potentials, not forces to solve. Think of a unitary matrix as being like the potential for a unistochastic matrix. To say a stochastic matrix is unistochastic is to say there is a potential for it, given by you. You may not be unique. After all, global phases are certainly allowed, and depending on whether it's block diagonal, there may be other non-uniquenesses you'll have with it, but super useful for calculating things. So think of a unistochastic matrix as like a conservative force, broadly metaphorically. You had a second question.
Yes. You said you were going to explain the pipe.
Oh, I skipped over that. Yeah, because I had to go. Yeah. So what's the pipe? One view, the view that David Deutsch took when he was figuring out quantum advantage, was he was a believer in many worlds, believed there were all these branches, and these branches motivated him to think about massive parallelism, and this, is what motivated him to think you could achieve quantum advantage. It turns out quantum advantage is actually very hard to achieve. It's not always obviously available. It's only available in very limited cases, and this is actually kind of surprising because if you think you have all these parallel universes at your disposal, it's kind of weird that you can only very occasionally make use of them. Nonetheless, he was inspired by the idea of these things to look for quantum advantage. Just like in the development of Maxwellian electromagnetism in the late 19th century, people said, ether is amazing. Ether is what motivated the stress energy tensor and motivated so much of the thinking that went into the development of electromagnetism. How could you deny there's an ether? I mean, it's so fruitful. It gives us a way to think about stuff. When we teach E&M, we use the ether all the time. It's a great pedagogical device. And yet, Einstein says, no ether. And we somehow moved on and weren't still stuck with this idea of the ether. I'm making the same claim about many worlds or the wave function. There are a lot of people who say that we need the wave function. It gives us an intuitive way to predict that you'll get double slit interference, or it gives us a way to think about why you would get computational advantage in a quantum computer. So how could we ever get rid of it? I'm saying that it's like the ether of the 21st century, or maybe the 20th century. Maybe, okay, I'm not sure. But that, and so it's no more, it's a piece of mathematics. It's a representational thing. It is no more real than Magritte's pipe. Cecine pas un pipe, right? People, and I have it in a ket vector because it's like a quantum pipe. But the point is, he had this painting, and this painting is from the 1920s, this fruitful period of the development of quantum mechanics. It's like timely, very timely, and people complained. They said, "You're being too glib. You're being too arch. What do you mean it's not a pipe? Of course it's a pipe." And his answer was, "Really, it's a pipe? Go ahead and smoke it." It is not a pipe, it is a representation of a pipe, and we shouldn't confuse a representation of a thing with a thing. Alfred Krobzinski said this very neatly, right? That one should not confuse a territory with the map of that territory. It's easy to make those confusions, and I'm saying we should avoid that. Just because the wave function seems like the primary object when you first introduced quantum mechanics doesn't mean we should take it seriously as a physical object. It turns out, from this point of view, to be a derivable secondary thing. That's just very useful for calculating, the way that an action is useful for calculating, or probably more better, a Hamilton-Jacobi function. In fact, the Hamilton-Jacobi functions of classical mechanics were the natural ancestors of Schrödinger's wave function. And we don't think the Hamilton-Jacobi functions are physical things. They're just useful mathematical tools. Yes.
So,
Well, you both asked questions before, so to break the symmetry, yeah.
So you went very, very quickly through the technical details, so I have a kind of naive question.
Yes,
So
we can talk about, if you want, I can show you this. You can also meet with me. I'll be around tomorrow. I'll be in that office tomorrow, so people can come and find me to talk. Yes.
So say I have a qubit.
Yes.
That has some simple Hamiltonian.
Yes.
Polymatrix. Should I imagine that the stochastic process in your version of it is valued on the Boolean set? Like what?
Yes.
What,
It's in the Boolean set, not the block sphere.
yeah.
Yes.
And it's
Think of it as an on-off switch.
Yeah.
It's got an on-off switch. In fact, I didn't show this because we ran out of time, but here is a classical analog model of a qubit. So if you thought qubits are just so quantum mechanical, there's no way you would ever imagine modeling them as anything else. Where is my qubit? Nope, that's not my qubit. Where's my qubit? Not my qubit, not my qubit. Yeah, there's a lot. These are all backup slides. You understand? I get so many questions. All of these are in response to not one, but at least two questions. If I've ever gotten a question twice, I make a slide for it, so I can show it to people. But yes, I'm now realizing you can see all of the insanity that is my life. Okay, so let's see. Where the heck is it? How do we? It's here. Here we go. Okay, good. This is it. So, okay. This is a classical analog model of a qubit. You could build it in the lab. I'm talking with some experimentalists to build this in a lab. It is no quantum mechanics in it, but it is mathematically dual to a qubit, and you could extend this to 2 qubits or 3 qubits and do entanglement experiments. Entanglement is supposed to be, Schrödinger said in 1935 paper, the one where he introduced the word entanglement in English, because he wrote in English as well as in German, that entanglement was not a, but the feature of quantum theory that most distinguished it from the classical case, but we can actually make entanglement in a classical system. Consider a black box experiment. It contains either of 2 possible classical systems, A or, it's a little bit of a weird experiment, but you can do it. Call the systems A or B. Each is a 2 configuration system, and they look pretty similar. Configuration 1 of A looks kind of like configuration 1 of B. Configuration 2 of A looks like configuration 2 of B. They're pretty similar looking. The difference is their energies. We'll concoct the experiment with magnets or whatever we need to do to make it so that the first configuration of A is the ground state, and the second configuration of B is the ground state, and they have the same energy difference between them. Okay? So basically, they're just inverted versions of each other, energy-wise. All right, now thermally couple this system to a reservoir with a gradually changing temperature that we can control. It's up to us to control this temperature as a function of time, with initial temperature 0. Then the Boltzmann occupation probabilities will give us a 2x2 stochastic matrix. It's all conditional probabilities. It's conditioned on whether we began in the ground state 1. This is if the system was A, because its ground state is 1, or if we began with system B. And maybe we don't know which the system began in, so there's a probability distribution whether it's A or B. And then these are the conditional probabilities. By symmetry, this is a matrix and it's a symmetric matrix and its diagonal entries are equal to each other. You could show that it is doubly stochastic, which just means its rows also sum to 1. Every 2 by 2 doubly stochastic matrix is provably unistochastic. You don't even have to rely on any special theorem for that. It's easy to prove. That means there exists a unitary. That means that we can think of this stochastic matrix as having a potential that is some unitary matrix. And from this, we get the Schrodinger equation, we get quantum mechanics, we get a whole quantum mechanical description of the system. It's cubic. And for specific choices of the conditional probabilities that you could get from tuning the temperature as you wish. For example, here's a very simple analytic, perfectly smooth, non-periodic analytic choice for the probabilities as a function of time. You can show that you get indivisibility and you can get interference effects and so forth. You can even compute amplitudes for the system, where you begin with the system in configuration 1, initial time, and you want to know the probability of measure, we'll find it in configuration 2 at the later time, and you do the standard thing. There's 2 possible paths you can take, where it's in intermediate state 1 or 2 at the intermediate time, but because this is an indivisible process, these are not probabilities, they're complex numbers, because you'll construct them, use the Hilbert-space formalism to construct them, it's fine. And then you can show, as we know, is you add and then mod square to get the correct probability. You can check that this works for the system. If you square and then add them, you get the wrong answer. And this is exactly interference. It is not just interference, it is the actual probabilistic type interference. This is not like, oh, quantum mechanics is like electromagnetism, it's got interference. This is probabilistic interference. This is the path integral. This is sum on paths that interfere with each other, even though we know the system is really taking just one path. The fact that we need complex numbers and that they interfere is a statement of indivisibility. It is not a statement that the system is truly exploring all of its paths. So you can, again, generalize this to multiple qubits. So, I mean, I got more models like this. Once you start looking for them, you find them everywhere. But this is a realizable system. We could actually build qubits in the lab. Non-H-bar qubits. Big, warm, macroscopic systems where we could begin to explore quantum mechanics. Yes, you had a question. Question, right?
Yes.
Yes.
I was just wondering, because in some sense here, because if you think about like pilot wave theory, every particle actually goes somewhere. But in your theory, if we look at the double slit experiment, if I understand correctly, like there still really isn't an answer as to whether the particle goes through the one slit or the other, because you're I mean, this is the whole point. The conditional probability doesn't sum up. Is that correct? Or
Let me nuance that answer.
okay.
So again, because of lack of time, I couldn't go through a detailed explanation of what happens in the double slit experiment when we consider all of its various permutations. So what is true is that in any given run of the experiment as done, we won't know which hole it went through.
Mhm.
According to this model, it did go through one hole or the other. I just don't know what it is because I don't have, I can say probabilistically which hole it's in, but I can't know for sure what hole it's in. Now, suppose I set up a detector and I put the detector near the holes. And this detector doesn't have to be a person. In fact, let's just totally let's de-anthropomorphize our detector. Let's make it a super simple 2 configuration detector that is in its rest configuration if the particle goes to the lower hole. And if the particle goes to the upper hole, it deterministically flips to indicate that it went to the upper hole. Right? And that's all it does. And maybe this detector, I mean, you don't have to, but suppose the detector is kept totally isolated. It doesn't, no environment comes in, nothing touches it. What you'll find is that the interference pattern goes away. It disappears. You can just check this. This is a calculation you could do. It's a little, I mean, I'll show you the calculation. It's like a few pages. To translate the stochastic picture into Hilbert-space language and do the calculation, and you get the right answer. What you can show is that the readout by the device generates a division event. And now we have well-defined effective laws that take the particle from the holes to the final answer. And that means we're going to be back under the assumptions that led to the disappearance of those interference effects. Now, if this device is coupled to an environment and the information that's recorded gets lost in the environment, then it is just you're not going to be able to undo this. But if the detector is kept very, very, very isolated, it doesn't talk to an environment or anything like that, and you've programmed it so that it undoes what it just learned in the time it takes for the particle to get to the projection stream, and the interference pattern comes back. And you can show this all works out without all those assumptions. So if your question is, if we actually measure where the particle is, we will find it in one place. Although the argument here is we're finding it in one place because it was in one place. We didn't have a true literal superposition that needed to be collapsed at any point. But if we do want to do a measurement on it, that's going to be a physical process, and that will deform the evolution.
Okay, but okay, but there is, because in pilot wave theory, for example, in
Yep.
principle, you could know which slip through the, I may not understand.
No, in pilot wave theory, you also can't know.
You can't know.
No. If you do a measurement in pilot wave theory, you're gonna decohere the wave function and you'll eliminate the interference. So in pilot wave theory, when you say you can't know, let me put it this way. In the pilot wave theory, sorry, go ahead.
So
Yeah.
I thought in pilot wave theory, in principle, if you knew the initial conditions of every particle in the entire universe, then you could just calculate everything.
And you knew the wave function in the initial universe.
Okay.
Yes, because that's part of the law, the wave function is part of the laws. Then yes, under those circumstances, you could predict
And
which holes.
there's no analogy in what
No.
you're talking about to
No.
that.
No.
Okay.
Yes.
So it's truly like, if the tree falls in the forest and no one hears, I don't know.
Well, no, quite the opposite. We're saying if the tree falls in the forest, it makes a sound. It's just, the sound is probabilistic. I mean, okay, so for a big macroscopic tree, you can show that for big systems, you get very reliably ordinary looking evolution. A big tree will make a normal sound. If a microscopically small tree falls inside of a microscopically small forest, it will do something. I don't know what it will do until I measure it. Yes, that would be a fair statement for this sort of thing.
Okay.
But the claim is that it doesn't do nothing and it also doesn't do everything. It does some particular thing. The Bohm theory is deterministic.
Yeah.
At the cost of introducing a lot of other machinery and running into problems of empirical adequacy when handling systems that go beyond those that consist of fixed numbers of finitely many non-relativistic particles. If you want to try to generalize the Bohm theory to more general theories, you want to do a lot of basic problems.